Bismillahirrahmanirrahim and Assalamu alaikum. I welcome you all to the lecture number 19 of electric circuit analysis. In this lecture today we are going to start chapter number 7, which deals with first order circuits. By definition, we define the first order circuits as the circuit in which we have the first order differential. You must have studied differentials and integral in calculus course. So you know that there are different orders of differential equation: first order, second order, third order. First order circuits are the circuits in which we have the differential at the first order, that is dV by dt or di by dt. RC and RL are the circuits, that is resistor capacitor circuit, and resistor inductor circuits are the circuits that we will be studying in this course. And when we study these two type of circuits, they produces differential equations. Differential equations of RC and RL circuit are known as first order equations or first order circuits. First of all, we have to see that when we have an RC circuit and it is source free, how and what is the response of the circuit. Free of independent source can be done as we assume that a source was attached to this RC circuit, and at any instantaneous time t is equal to 0, the source was turned off. This means that the capacitor has been charged with its initial charge, and it is I is equal to C dV by dt. A source free circuit occurs when the DC source is suddenly disconnected. This means that the capacitor has been charged at t is equal to 0. For example, I have this voltage connected to this RC circuit, and when we disconnect this voltage, that is, the switch is open, there is no more applied voltage to this circuit, and we are only left with the standard RC circuit just shown to you. Now, to find the circuit response of this force-free RC circuit, we assume that Vt is a voltage across a capacitor at time t is equal to 0, and which we turn as V of 0 at time 0 is equal to V naught. So if we have to find the energy stored in the capacitor, which you know from 6th chapter, the previous chapter, that the energy is W is equal to 1 by 2 CV square. So if I am taking at time t is equal to 0, then this V of 0 is replaced by V naught square. So this is 1 by 2 CV naught square, and this is the resultant circuit by removing the external voltage source at time t is equal to 0. Now if we want to find the response of this circuit, we apply KCL at this node. You can see that the current is moving, IC current is in the downward direction, and IR is going to this direction. So we have no incoming current, and both are leaving current. So by KCL, I entering the node plus I current leaving the node must be equal to 0. The sum of the two should be 0. So the equation is IC plus IR is equal to 0. Both the capacitor current and the resistor current are leaving. IC, the capacitor current, is given as C dV by dt, and IR is given by Ohm's law, which is by V over R. So the KCL equation becomes IC plus IR is equal to 0. We insert in the value of the capacitor current and the resistor current, and we get to know that this is C dV by dt plus V over R. Now, by arranging the equation in such a manner that we multiply this equation on both sides by 1 over C, so this C cancels out from here, and we are left with this form of the equation: dV by dt plus V over RC. This is the first order differential equation, since you can see that the voltage has first order derivative. Now what we do is we rearrange the circuit, dividing both sides by V. So first of all, we take this entire term over here minus 1 over RC, since it was plus. By changing the position across the equality, the sign changes to minus. Now dividing both sides by V, what we get is we rearrange the equation, and it is dV by V. Now further multiplying both sides by dt, we get the resultant form of the equation as dV by V, by collecting the V terms on one side and the rest of the constant terms on the other sides. Now we integrate both sides of this equation, and as you know that by the rule of integration, that the derivative of a function is in the numerator and the function is in denominator, so it will be equal to natural log of V, natural log of that function. So what we get is dV by V minus 1, as 1 over RC is a constant, so integral won't apply over it. So this term equals to natural log of V, and this is minus 1 over RC, and integral of dt is t, so plus constant of integration, a natural log of a is constant, integration constant. When we take this term to this side, you know that natural log, instead of putting a minus sign, it is divided natural log of v over a. This becomes natural log of v minus natural log of v. It becomes natural log of v over a minus trc. This is the same term. So now taking in order to finish off this natural log, we have to take the power of exponential on both sides, and these two natural log of and exponential term, they cancel out each other, and this raised to exponent, this is now the exponent of the exponential e, my e raised to power minus trc. Now v over a is e raised to power minus trc, and you know that a, when we multiply it by both sides, v of t gets a e minus trc. Now as you know that a was a constant of integration, and over here we take as initially we had the voltage at time t is equal to 0 is equal to v naught. So instead of a, we put in the value of v naught, and the standard equation for an RC circuit, source free RC circuit, that we get is v of t is equal to v naught into e raised to power minus trc. This is the natural response of a circuit which does not have any external source of excitation, any potential. So the voltage response is that at time t is equal to 0, we have the voltage v naught, and the response decays with time t, and the exponential function is shown as like this. The time at which the value of voltage becomes 0.368 into v naught, it is called as time constant, and time constant is given as t is equal to rc over here. So this is the time in which the voltage finally left is 1 over e, or 0.368 of the initial value, that is v naught. If we replace rc in place of tau, so what we get is v naught minus trc is now v naught into e raised to power minus t by tau, and tau is the product of resistance and capacitance in the circuit. Now for a capacitor to get fully charged or fully discharged, the time that it requires is t is equal to 5 times tau, that is 5 times the value of rc, or 5 times the value of time constant is the time that a capacitor takes in getting fully discharged or fully charged. Now once we know the voltage across the circuit, we can easily find the current, which is IR is equal to V over R. By inserting it the same value, since both are in parallel, so we simply divide the V value by R and we get to know the current in the circuit. This is all for this lecture. In case you have any questions, please do let me know. It was simple derivation of an RC circuit in a sourceless mode. Thank you. Best of luck.